Okay, let's do another duality example so that we can get some practice with it. Here's a minimization problem, and we want to go ahead and make a corresponding dual problem. And then actually we're going to solve that dual problem graphically. So if you look at this problem, we got four variables, and I don't know about you, but I can't graph worth a lick in 4D. Can't even think in 4D really, since we're limited 3 dimensions. And so not couldn't solve this graphically as is. But if I transform to the dual problem, since the primal has two constraints, the dual problem will have two variables, and that is something that I can solve graphically. Uh, and so yeah, we can kind of take advantage of more constraints and fewer variables if we move from one to the other. And actually, algorithmically though, constraints cost more in solving than variables. And so actually, most of the time, your solver will do the opposite, where it will try to switch between primal and dual to get fewer constraints, but potentially more variables. So let's do that. So we got a minimization problem. So our dual problem is going to be a maximization problem. And we're going to maximize W equals. So I'm going to label each of these rows with my two new dual variables. So Y1 and Y2. Okay. And really, I can read off the coefficients that I'll get for Y1 and Y2 from the primal problem's right-hand side. And so it'll be 2Y1 plus 3Y2. Okay, that's not too hard. Now, what I do is I kind of, each constraint in my dual problem will correspond to a variable in my primal problem. And so let's essentially circle the X1 column through here. And that's going to have coefficients of 1 in the Y1. And so 1 Y1 and 2 in Y2. And then a right-hand side of 2. And these are going to be maximization problems because the original constraints were minimization with greater than. These will be maximization with less than or equal to's. Okay, and that's going to be essentially you think of that as the X1 constraint. Okay, now let's do the same thing with X2, and we'll circle the column that has all the X2 values in it. And I'll read off that there's 6 in the Y1 row and -5 in the Y2 row is less than or equal to, there's 15 in the old objective row, and that becomes the new right-hand side. And so that is the X2 constraint. Let's look at X3. I'll circle all the X3s there. And so 3 in the Y1 plus 4 in the Y2 is going to be less than or equal to 5 in the old objective row. And that's going to be our X3 constraint. Now I've got just enough colors to do this. We'll circle all the X4s. And we'll have 1 in the Y1 and 3 in the Y2. Oh, that's actually a -3. Almost missed that because of my circling there. And that's going to be less than or equal to, we had a 6 in the objective row before. And that's going to be the X4 constraint. Okay, so each primal constraint corresponds to a dual variable. Each primal variable corresponds to a dual constraint. Okay, so now this is a setup where I've got 4 variables, 4 constraints, but now only 2 variables. And so I can go ahead and graph this. I'll go ahead and graph this in Desmos. So let me just switch the share to Desmos. And so here are those 4 constraints. I've Desmos only thinks of its variables as X and Y. And so the first Y1 is actually labeled X here and Y2 is labeled Y here. Here's those constraints. My feasible region is the region that satisfies all of them. And so it's going to be this region right here. I'm going to have corner points of 0, 0. I'm going to have a corner point right here of 1 2/3, comma 0, so 5/3, 0. I'm going to have a corner point here at 1, comma 1/2. And then I'm going to have another corner point here of 0, comma 1. So I'll go ahead and copy down this graphical picture down onto the paper and we'll solve it graphically. Notice that we've got two constraints that are sort of off over here that keep this whole region, it's still feasible, but these constraints are way off and not really actually affecting the solution at all. So pause the video and let's see. Yeah, pause the recording, copy down this to the sheet. Okay, I've copied down our kind of picture of our feasible region. Here's our feasible region. I've gone ahead and labeled those corner points, which we know now are basic feasible solutions. Only the two constraints for X1 and X3 end up being in the picture. The X2 and X4 constraints sort of end up being off to the side out of the picture. And so I didn't end up drawing them in there. They don't actually touch the feasible region. So here are my four basic feasible solutions. I can now, and these are values for Y1 and Y2, right? So that's actually, my axes here are the Y1 axis and then the Y2 axis there. And so I can plug those into my dual objective here. Plugging those in, 0 and 0 will give 0. 0 or 5/3, 0 will give a value of 10/3. 1 and 1.5 will give a value of 2 plus 3.5, which is 7/2. And then 0, 1 will give a value of 3. And so kind of this is about 3.33. This is equal to 3.5 versus 3 down here. And so the dual problem is a maximization problem. And so we want to choose the largest. And so this is going to be our optimal dual solution. Okay. So let's see if we can use complementariness or complementary solutions to bring this back to a primal solution, right? Because to be honest, usually people aren't as interested in the dual solutions. It does give you the shadow prices. And so our first constraint has a shadow price of 1. Our second constraint has a shadow price of 1/2 in the original problem. But we want to get back and actually figure out what are the values of X1, 2, 3, and 4. Okay, so let's use complementariness for that. And so here, I'll go ahead and write down dual. And then, because this time we got information from the dual and we're going to move towards the primal. That in the last example with Geppetto, we had the information from the primal and we're moving towards the dual. So here now we'll look for a primal complementary solution. So what do we know? Well, we know our dual solution. Our dual solution is y1 equals 1. And that's a positive amount. And y2 equals 1/2. And that's also a positive amount. Okay. And so if the dual variables are positive, not 0, that tells us that the corresponding constraints have no slack. And so the y1 constraint in the primal problem has no slack because the slack times the variable has to equal 0. The variable is non-zero, so the slack must be 0. And so there's no slack. That y1 constraint is this first constraint here. And so that tells us that x1 plus 6x2 plus 3x3 plus x4 is not just greater than or equal to 2, it's exactly equal to 2. Okay, so having no slack changes an inequality into an equality. Okay, and we can say the same thing for the y2 constraint. Because y2 is positive, the y2 constraint has no slack, which tells us then that the second constraint in the original problem, this one, is going to be an equality. And so 2x1 minus 5x2 plus 4x3 minus 3x4 is not just greater than or equal to 3, it's exactly equal to 3. Okay, so that's two useful pieces of information. Now we got two equations, but we still have four unknowns. So we need at least two more useful pieces of information, and that will come from the slack. Okay, and here's where we're actually going to use things pictorially here. So this, our optimal solution is this one right here. It's on the boundary of the x3 constraint, and it's on the boundary of the x1 constraint. And so both those two constraints have no slack. Okay, so I'll say this one as x1 slack equals 0, and x3 slack equals 0. Okay, they're 0, which means that the corresponding variable in the primal just tells us that x1 is greater than or equal to 0 and x3 is greater than or equal to 0. Not informative, or not very informative. You can kind of get something from it, but nothing more than what we maybe knew initially, because we kind of constrained these to be greater than or equal to 0, non-negative from the beginning. Okay, so that's going to be the less useful ones. But what we'll notice is that this point is not on the x2 and the x4 constraints. Those constraints are actually running way out here outside the picture. And so x2 and x4 constraints will both have slack. And so I'll write that down here, that the x2 slack is going to be a positive amount of slack, and the x4 slack is going to be a positive amount of slack. And because we're off those two constraints, we're not on the boundary of them, that then forces x2 to be 0 and x4 to be 0. Okay, and so we have four primal variables. We now have four equations. Essentially, two of them zero out two of the variables. And so that allows us to x2 and x4, I can go up here and I can zero that out, zero that out, zero that out, and zero that out. Okay. Which if I bring all this down, so I bring this down here, bring this over, I'm left with then x1 plus 3x3 equals 2, and 2x1 plus 4x3 equals 3. Okay, now it's down to two equations, two unknowns. I could turn this into a matrix, but I could just as well kind of add and subtract these equations from each other. So I'll do second equation minus the first, so plus this minus that, and we'll get 2x1 minus 1x1 will give us x1, and oh no, I'll do negative 2 times this one, so that I get 0x1. So I'll do plus 1 times the bottom row, negative 2 times the top row, and that will then give me, so that will zero that out. I'll then have 4, negative 2 times 3 is negative 6. 4 minus 6 is going to give me negative 2x3, and 1 times 3, negative 2 times 2 is going to be equal to negative 1. So 3 minus 4 is negative 1. And so negative 2x3 is equal to negative 1, or x3 If I divide by -2 is then going to be +1/2. And then I can plug that into either of these up here, and I'll get that x1. Let's see, I'll plug it in here. I'll get 3/2, subtract that over the other side, and I'll get that x1 is actually also equal to 1/2. Okay, and so my full solution now is that to my primal problem is that x1 equals 1/2, x3 equals 1/2, x2 and x4 are equal to 0. Okay. Also, let's check our objective value. So our original problem, we wanted z, and we wanted to minimize 2x1 plus 15x2 plus 5x3 plus 6x4, which now plugging the values in that we've got is going to be 2 times 1/2. This is 0 and this is 0. So then we get plus 5 times 1/2, and we get 2/2 plus 5/2 is 7/2, which is 3.5. Notice this is the exact same objective value as we got for the dual problem. Dual problem, we're maximizing and we chose 3.5. This actually ends up being the minimum value for the primal problem. So complementary solutions, if you solve one, then you can solve the other. And sometimes it's easier to solve one than the other. And so you can take advantage of duality to help you out there. Okay, there will be other applications of duality that we'll see along the way as we get into sensitivity. But this kind of concludes the section on duality and what you can do with duality, at least until we start applying it when we start talking about sensitivity. So that's it for this video.